Hey, I wanted to make a video of this for you guys. This is this one. Just to kind of talk through how to do it, make sure that everybody is on the same page and you get some help if you need it. So the first thing we need to do with this graph, it looks really intimidating because it's got a lot of lines to it, but we have kind of big numbers that we're dealing with here. So it's going to be helpful in that way to make sure we can fit it all on there. So the first thing we need to do is figure out what our scale is going to be. So I noticed that the seconds needs to go up, and seconds time is always going to be on the x-axis because it's setting the pace. So the seconds needs to go up to 200, and the y-axis, meters, needs to go up to 100. So I just came down here and I counted. First I did 10, 20, 30, 40, 50, 60, 70, and I got up to 100 right about here. So I knew that wasn't going to be big enough. So then I tried 20, 40, 60, 80, 100, and that worked out well. So went up by 20s. I'm making sure to line up my numbers with the big lines here. And then I went ahead and labeled seconds right underneath. And then the trick that I did here is I just said duplicate, and I flipped it over, and this, the y-axis, just needs to go to 100, so I counted 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, and that fits well there. So that's what I did for that one. Okay, so when we're looking at this data, let me just show you what it looks like here. So we've got 20 seconds, 10 meters. We got 40 seconds, 20 meters. We got 70 seconds, 35 meters. Let me fix this a little bit. I could say duplicate, 70, 35, duplicate. So then we got 130, 65, 170, 85, and 200 seconds, 100 meters. And what I should have been saying there as I was doing that, because it's helpful, anytime you're working with science, we're working with real things, right? We're working with like stuff that we can really like see and handle and stuff. So I think that always saying the units as you're doing this is a really helpful way to keep yourself grounded and connected in that way. So, so it looks to me, as I'm looking at this chart, like the meters are always half of the seconds. So that's going to come up in just a second when we're looking at these next questions. Oh, so I labeled the graph, meters and seconds, got my numbers, title was already there. I inserted the data, and I'm going to draw the line of best fit. So here it comes. I'm going to do blue. I'm going to make it thick. Actually, let's try this one. Okay. Oh, I don't like that one. I want it to be darker. So this line goes up pretty straight up that way. Okay, next one. So does our graph represent constant velocity or changing velocity? So this looks pretty constant to me. If it was changing velocity, then you would see it go up at a steeper slope sometimes and maybe down at a slope sometimes, maybe flat sometimes. But this is very consistently going up at a rate of about 1 on the x, or 1 on the y-axis to 2 on the x-axis, 1/2. Okay, so constant velocity, and I know because the slope of the line is consistent. Again, if that slope was changing, then that would be a changing velocity, but it's constant. So what is the average velocity here? So when I'm looking at average velocity, whenever velocity or speed is always going to be your slope, right? It's your meters per second or your kilometers per mile or always your y-axis over your x-axis. So here, this is my y-axis, and this is my x. So I can actually just look at these numbers and see this. It's going to be 10 divided by 20, 20 divided by 40, 35 divided by 70. They're all like these numbers are 1/2 of that. So that's going to be 0.5 meters per second. And since it's constant, easy peasy. Okay, so now let's look at this one. We're going to move the yellow letters to match the description with the line of best fit in the graph to the right. So when we have something that's at rest, that means that as time is increasing, that y value is not changing. The position is staying the same as time is going by. So at rest is going to be C. When we are traveling slowly in a positive direction, positive meaning that that slope is going to be positive, meaning that the line is going to go up, but it's traveling slowly, so that position is not going to change very much over the course of time. So that's going to be D. See how that line it's moving, but it's moving just a little bit at a time. As opposed to traveling quickly in a negative direction, this is like this one where it's starting high, going low. A negative direction meaning that we can think of it also as an inverse relationship, where as time is going up, the y values are going down. So A for that one. Traveling fast in a positive direction, it's going to be B. It's not traveling as fast as the negative direction one, but it is traveling pretty fast compared to the other one. So again, whenever we're talking about velocity or speed, we're talking about slope. Kilometers per hour, miles per second. Well, miles per second would be like space things. Okay, so given the position time graph below for a person walking, answer the following questions. During which intervals is she moving in a positive direction? So again, a positive slope is that direct relationship. As time is going up, the distance is also going up. So A is a positive direction, B is where she's holding still, C and D is a negative direction, and E is a positive direction again. So A and E. So during which intervals is she moving in a negative direction? So a negative direction is where as time is going up, the distance is going down. So C and D are both negatives. Okay, so now what distance did she walk during the first 10 seconds? So here's 10 seconds right there, and I see her going from 0 to 60. So she walked 60 meters. And the meters is marked there. Meters. 60 meters. How far displaced was she? So when we're talking distance, it's like all of these added up together. This one was just the first 10 seconds, so it's just this one. But displacement is just like to take a snapshot, where they start and where they end. At 40 seconds compared to here, she is negative 40 meters from where she started. So you can think about this as like she's really just traveling in a line. She goes forward a bunch of steps, and then she goes backward a bunch of steps. So 40 meters, negative 40 meters here. Okay. And again, with displacement, we can show distance, or we can show that whether it's like a positive or negative value, whereas distance is always going to be a positive number. It's just like how many steps you can. You can't take negative steps, but you can go in a negative direction. So displacement can be negative, or it can be in a certain direction. Okay, here's some more questions for this graph. What was the person's velocity during interval C? So interval C is like whenever we're talking about velocity, again, it's the slope. So we need to find the rise over the run, the y over the x. interval C. So I see that interval C starts at 15 seconds and stops at 30 seconds. So that's 15 seconds for the X. And she is going negative 60 for the Y. So let me write that out on a thing here. So we got negative 60 is our rise. She's going down, or she's going back towards the start 60 meters. 60 meters divided by 15 seconds. Let me pull up my calculator real quick for that. 60 negative divided by 15 equals negative 4 meters per second. So I better write that in here. Negative 4 meters per second. During interval E, so I see that she's also traveling for 15 seconds here. So there's 3 chunks. And it looks like she's going from negative 40 up to 0. So that's going to be moving by positive 40 there. So let me say duplicate here. So let me show you what I did there. So talking rise over run. So we have a movement of going up by 40 meters in 15 seconds. So let's see what that is with our calculator. 40 divided by 15 is going to be 2.67 meters per second. If she was going down, or if she was going farther back towards the, well, I guess that's kind of a confusing way to say that. Since she's going from negative 40, since the slope is positive, that's why we've got that positive 40 there. But since here the slope was negative, that's why we've got negative 60, going back towards the start and then going closer to the start. Okay, so what is the total distance she traveled in 55 seconds? So I see 60 meters there plus another 60 meters there, so 120, plus another 40 meters there, so 160, plus another 40 meters there. So that's going to be 200 meters. Distance is always going to be a positive number because it's like the number of steps that you take, how long your path is. So 200 meters. And her displacement after 55 seconds is actually 0 because she's ending up right where she started. If we were looking at here, her displacement would be negative 40. If we were looking at here, her displacement would be positive 60. But right there, her displacement is 0. 0 meters. Okay, so that's that one. There you go.